In September 1939, as the first air raids of the new war unfolded over Poland and China, and later over Western Europe, the man who observed air defense from within the military system saw a fundamental imbalance already forming, one that numbers and regulations could not hide. Anti-aircraft artillery, inherited from the doctrines of the First World War and the interwar years, was designed to confront slow, predictable aircraft flying at steady altitudes, not fast, massed formations attacking from multiple vectors. Guns had improved in caliber and mechanical reliability, but their effectiveness still depended on two primitive solutions: contact fuses that required a direct hit, and time fuses that demanded near-perfect prediction of an aircraft's future position. The mathematics behind these fuses assumed stable flight paths and limited speeds, assumptions that no longer matched reality by 1940. By 1941, the problem had become undeniable. During the attack on Pearl Harbor on 7 December, American anti-aircraft batteries fired more than 8,000 rounds in the first hours of combat. Only a handful of Japanese aircraft were damaged by ground fire, while hundreds of shells detonated harmlessly in the air or failed to detonate at all. Time fuses were set manually based on estimated altitude and speed, calculations performed under stress, often seconds before firing. A small error in fuse setting translated into a miss measured in tens or hundreds of meters. Contact fuses were even more unforgiving, requiring a direct impact on a target moving at over 300 kilometers per hour through three-dimensional space. The consequences were not limited to military inefficiency. In Britain, during the Blitz of 1940-1941, falling anti-aircraft shells caused thousands of civilian casualties. British records from 1941 indicate that in some urban areas, more civilians were injured by returning shell fragments than by enemy bombs during certain raids. The man studying these reports understood the grim irony. Defensive fire meant to protect cities had become another source of destruction. Guns filled the sky with steel, but the sky remained largely under enemy control. Across all theaters, ammunition consumption rose to unsustainable levels. In some Pacific engagements in early 1942, naval task forces expended thousands of rounds to achieve a single confirmed aircraft kill. Fire control systems improved incrementally, but the underlying flaw remained unchanged. Anti-aircraft warfare relied on predicting the future position of an aircraft rather than reacting to its actual presence. Against faster aircraft, steeper dive attacks, and later evasive maneuvers, this approach collapsed under its own assumptions. By the end of 1941, the man could see what official communiques avoided stating openly. Air defense as it existed was fundamentally inadequate. Guns were powerful, crews were trained, and ammunition was plentiful, yet the results did not justify the cost. Somewhere between the mathematics on the firing tables and the reality of the sky, a decisive gap had opened. Closing that gap would require abandoning a principle that had guided artillery for decades and replacing it with something that, at the time, still sounded impossible. By 1940, while reports from Europe and Asia accumulated on desks in Washington, the man following the technical side of the war noticed a quiet divergence between frontline reality and theoretical possibility. The failures of anti-aircraft fire were no longer disputed, but the solutions proposed by most committees remained incremental: larger calibers, higher rates of fire, improved predictors. Against this background, one idea resurfaced that had existed only at the margins of physics laboratories since the 1920s: the concept of a fuse that would detonate not on contact and not by time, but by proximity to the target itself. The principle was simple in theory and almost absurd in practice. A shell would carry its own miniature radio transmitter and receiver, emit a signal during flight, detect the reflection from a nearby aircraft, and trigger detonation at the moment of closest approach. In the technological environment of the late 1930s, this bordered on fantasy. Vacuum tubes were fragile, radio components were bulky, and artillery shells experienced acceleration forces exceeding 20,000 G at firing, followed by rotational speeds of tens of thousands of revolutions per minute. Any electronic device placed inside such a shell was expected to disintegrate before leaving the barrel. The man knew the name most closely associated with challenging this assumption, Merle Tuve. A physicist with experience in radio wave propagation and experimental electronics, Tuve had been working at the Carnegie Institution of Washington when war accelerated the pace of applied research. By late 1940, with American rearmament underway, Tuve and a small circle of scientists began arguing that recent advances in miniature vacuum tubes, originally developed for hearing aids and portable radios, might survive conditions previously considered impossible. Skepticism dominated the early discussions. Engineers pointed out that even if a tube survived launch, it would have to function reliably while spinning at extreme speed, powered by a battery small enough to fit inside a shell, yet robust enough to remain active for minutes. Others noted the danger of accidental detonation near friendly forces, ships, or even the gun barrel itself. A malfunctioning proximity device could destroy the weapon firing it, a risk no Navy or Army could accept lightly. Despite this resistance, the pressure of events reshaped priorities. By 1941, the United States Navy faced aircraft attacks that existing defenses could not counter efficiently, and the Army watched British struggles against air raids with growing concern. The question shifted from whether the idea was elegant to whether it could be made to work at all. The man saw how the language changed in memoranda. Phrases like theoretically unsound were replaced by technically challenging and then by requires urgent investigation. What made the concept seem impossible was not a single obstacle, but the accumulation of them: miniaturization, survivability, power supply, reliability, and safety, all of which had to be solved simultaneously, not sequentially. Failure in any one would render the entire system useless. Yet by the end of 1941, with the United States now fully at war, impossibility was no longer a sufficient argument. An idea that could not exist in peacetime had entered a world where necessity outweighed precedent, and where failure carried a cost already measured in burning ships and shattered cities. By early 1942, the man observing the American research apparatus could see that the proximity fuse had moved beyond debate and into an institutional structure designed for wartime speed. The work was consolidated under a deliberately obscure designation, Section T. The name concealed its purpose even from many within the military bureaucracy, reflecting a level of secrecy that matched the sensitivity of the task. Section T was not organized as a conventional laboratory, but as a pressure-driven system, where physics, engineering, and manufacturing considerations were forced to evolve simultaneously rather than in sequence. The operating principle of Section T was blunt and pragmatic. Perfection was explicitly rejected as a goal. Devices did not need to be elegant or theoretically optimal. They needed to function reliably often enough to justify mass production and combat use. The man noted how this philosophy clashed with academic instincts. Circuits were frozen before exhaustive testing, tolerances were widened rather than narrowed, and components were selected not because they were ideal, but because they could be produced in the tens of thousands without interruption. James Van Allen emerged as a central figure in resolving one of the program's most critical obstacles, the vacuum tube. Standard radio tubes shattered under launch acceleration or failed after seconds of operation. Van Allen focused on redesigning tube geometry, shortening internal leads, reinforcing filament supports, and potting components in shock-absorbing compounds. These changes reduced sensitivity to vibration and centrifugal force, allowing the tube to remain functional while spinning at over 20,000 revolutions per minute inside a shell traveling at supersonic speed. Deadlines dominated every decision. Field commanders demanded results measured in months, not years, while industrial partners required stable designs to tool production lines. Section T imposed rigid testing cycles, sometimes accepting failure rates that would have been unacceptable in peacetime engineering.
The man studying internal reports saw how a single modification, such as changing the thickness of insulating material or altering the placement of a solder joint, could determine whether a fuse survived firing or failed catastrophically. Coordination between scientists and manufacturers became decisive. Designs were continuously adjusted to match what factories could actually produce under wartime conditions. When a component proved too delicate for assembly line workers, it was redesigned rather than replaced with a better but unavailable alternative. This approach sacrificed theoretical efficiency for operational certainty, a trade-off made consciously and repeatedly. By mid-1943, Section T had transformed an idea once dismissed as impossible into a working system that survived firing, functioned in flight, and detonated within meters of an aircraft. The man understood that this success did not come from a single breakthrough, but from an organizational choice to prioritize speed, sufficiency, and adaptability over refinement. The fuse was no longer a laboratory curiosity. It had become a weapon, shaped as much by time pressure and industrial limits as by physics itself. And its first true test was no longer theoretical, but imminent.
By late 1943, the man following the program could trace a clear transition from experimental success to industrial reality, a shift that proved as difficult as the original scientific challenge. The proximity fuse that emerged from Section T was no longer a fragile prototype, but a defined device, compact enough to fit inside standard anti-aircraft shells and robust enough to survive the violence of firing. Its operating principle was direct and unforgiving. Once fired, the shell activated a miniature radio transmitter that emitted a continuous signal forward. When the signal encountered an aircraft, part of it reflected back to the receiver within the fuse. As the shell approached the target, the strength and frequency of the reflected signal changed, and at a predetermined threshold, the circuit closed, triggering detonation at the point of maximum lethality. Testing revealed how narrow the margin for error remained. Early versions detonated prematurely near waves, rain squalls, or even large birds. Others failed entirely when electronic noise overwhelmed the receiver. Safety systems were added incrementally, setback switches that armed the fuse only after the shock of firing, delay mechanisms that prevented detonation near the gun, and filters that rejected false reflections. Each addition reduced risk but increased complexity, and complexity threatened production speed. The balance was constant and uneasy. Scaling production required an industrial mobilization comparable in secrecy and intensity to the most sensitive wartime projects. Factories were compartmentalized so that workers assembled individual components without understanding their function. Women made up a large portion of the workforce, selected for manual precision and trained to assemble miniature circuits under strict quality control. By 1944, millions of fuses were being produced, each tested electrically but never fired before shipment, a calculated risk accepted to meet demand. Security measures were extreme. Technical drawings were classified, shipments were disguised, and combat units were initially forbidden to use the fuses over land for fear that unexploded examples might be recovered intact. The man recognized that this restraint reflected confidence mixed with fear. Confidence in the weapon's potential, fear of losing its advantage through premature exposure. What emerged from this process was not merely a scientific instrument, but an industrial system capable of delivering advanced electronics at unprecedented scale under wartime conditions. The proximity fuse represented a convergence of physics, engineering, labor, and secrecy, all driven by the same imperative. It was proof that victory depended not only on ideas, but on the ability to transform those ideas into reliable weapons faster than the enemy could understand them. The final question was no longer whether the fuse worked, but what would happen when it met the enemy for the first time.
In early 1943, the man examining after-action reports from the Pacific could identify the moment when theory crossed into irreversible fact. The first combat deployment of proximity-fused ammunition occurred quietly, without public announcement, in a theater already defined by air attack and attrition. Naval commanders were instructed carefully, and use was restricted to open water, where the risk of unexploded fuses falling into enemy hands was minimal. The first ships equipped with the new ammunition entered combat during the prolonged struggle around Guadalcanal, where Japanese aircraft repeatedly attacked Allied surface forces operating under constant threat. One of the earliest documented engagements occurred aboard the light cruiser USS Helena in January 1943. During Japanese air attacks, the ship's anti-aircraft batteries opened fire using shells fitted with the new fuses. Observers noted an immediate and measurable change. Aircraft that previously passed through dense barrages emerged unscathed, now detonated shells in close proximity, shattering control surfaces and engines without requiring direct hits. Japanese pilots reported explosions occurring where no contact had been made, a phenomenon for which they had no explanation. The statistical impact was unambiguous. U.S. Navy analysis later showed that anti-aircraft effectiveness against dive bombers and torpedo planes increased by a factor of 4 to 5 when proximity fuses were employed. Ammunition expenditure per kill dropped sharply, and defensive fire became denser, not in volume, but in effect. As the war progressed into 1944 and 1945, this advantage proved decisive against kamikaze attacks, where aircraft were intentionally flown into ships at high speed and low altitude. Proximity fuses allowed defensive guns to destroy or cripple attackers seconds earlier than before, often far enough from the ship to prevent catastrophic damage. The Japanese response lagged behind reality. Pilots and intelligence officers initially attributed losses to heavier fire or improved gunnery training, not to a new technology. Wreckage recovered from downed aircraft offered no clues, as the fuse detonated with the shell. Without intact examples to study, Japanese engineers could not identify the mechanism responsible. The man reviewing captured documents saw how reports described unusual bursts and air explosions, but failed to connect them to electronics-based detonation. At sea, the proximity fuse altered the balance of survivability. Ships that would previously have suffered repeated hits now repelled attacks with fewer casualties and less damage. The change was not dramatic in appearance, but cumulative in effect. Each failed attack preserved a ship, its crew, and its mission. By the time the enemy began to suspect that something fundamental had changed, the weapon had already proven itself across hundreds of engagements, and its true significance was only beginning to extend beyond the ocean.
By the summer of 1944, the man studying Allied operational decisions could see that the proximity fuse had crossed a final threshold, one defined not by engineering but by trust. Until that point, its use had been deliberately restricted to naval warfare, where shells detonated over water and left no recoverable remnants. Europe forced a reconsideration. German V-1 flying bombs were striking Britain in large numbers, and conventional anti-aircraft fire remained inefficient. Time-fused shells often detonated too early or too late, while direct hits against small, fast targets were rare. Ammunition consumption was extreme, and interception rates remained unacceptable. In July 1944, British and American authorities authorized the first land use of proximity fuses under strict conditions. The results were immediate. Anti-aircraft batteries defending southern England increased their V-1 destruction rate from roughly 15% to over 70% within weeks. The same guns, crews, and radar systems suddenly produced radically different outcomes. The fuse, not the weapon, had changed the equation. For the first time, air defense reacted to the actual presence of the target rather than a prediction of its position. This success led to another critical decision. During the German Ardennes offensive in December 1944, proximity fuses were issued for use in ground artillery. Fired above advancing infantry, shells detonated at optimal height, producing airbursts that bypassed trenches, snow cover, and forest concealment. American after-action reports described German units suffering severe casualties even when dug in, their traditional defenses rendered ineffective. The man reviewing these documents noted how the fuse transformed artillery from a weapon dependent on terrain into one that neutralized it.
The strategic implications were profound. The proximity fuse multiplied the effectiveness of existing weapons without requiring new guns, new crews, or new doctrine. It shortened engagements, conserved ammunition, and reduced friendly losses. Axis powers never replicated the technology, not because the physics were unknown, but because the industrial, scientific, and organizational systems required to produce millions of miniature electronic devices under wartime pressure did not exist within their economies. By 1945, the fuse had altered air defense, naval warfare, and artillery employment across multiple theaters. It did not end the war alone, but it changed the terms under which battles were fought. The man understood its true significance lay not in any single engagement, but in what it revealed about modern warfare. Victory now depended not only on firepower or courage, but on the ability to integrate science, industry, and secrecy faster than the enemy could respond. The proximity fuse was not merely a weapon, it was a demonstration of how wars would be decided from that moment forward.